the floor to questions for our panel. We've got a couple that have already come in, and I'm going to sort of direct those, and I have a few myself as well. But to start with, we have one directed straight for Veselin. I think this is given your unique area of doing both VRFBs and lithium ion. What do you see the competition between lithium ion and VRFB going forward, Veselin? How do you see that competition?
I think the competition is mainly in prices, but as we are talking more about storage projects and they're taking more importance today, we are seeing that on 20 years based project, we can compete with the lithium on price. So in projects up to more than 4 hours, we can completely compete with the lithium. Of course, the market is more based on lithium. The capacity of production for lithium batteries is much higher than vanadium, and the complete industry is more prepared for lithium. So that is an advantage for the lithium. But I think the vanadium redox flow batteries have the place into the market, and we need to work on it to develop more and more business opportunities for this and the next years. So I think we are competing with lithium, and as a company, we need to choose always the best solution. And the capex is something that is an indicator for the customers, but a lot of the times we can convince the customers with the technical capabilities of the vanadium flow batteries.
Great. Maybe I'll open up to Alexander or Tomas if you have any comments there on also on VRFB versus lithium ion, or we also have questions for any of you on a hybrid approach of using both.
Yeah, happy to give an answer. Before I was CellCube, I was in Unicos deploying lithium systems. So what I see is that the mix of both does make sense commercially, only if you are able to combine use cases. So if you're in front of the meter space, then you must have different use case scenarios to maybe switch between them, or that you are able to use them really for, like, say, on a sensor basis, like whenever there's a peak power request, you're able through your control system to allow the lithium ones. So it's really a very enhanced and comprehensive BMS required to allow this, and therefore I think it makes it very difficult to deploy those hybrids in front of the meter. The other thing is, if you're behind the meter, we see also that it can make sense. And I think this is where you are able then to really run multiple use cases at the same time. At the end of the day, and so far, there is not really a commercial market for those multi-use cases, unless, like I said, you're in a private situation and then, you know, there's a client saying, I have that use case A for energy shifting, and use case B for participating in the market, and C for any kind of other kind of power requirement. But this is very rare, and I think therefore it will take some time to see those hybrid cases. It's too risky. I think it's still two asset classes which are not yet kind of fully accepted by every investor. So small scale always possible, large scale probably not yet bankable.
Tomas, anything you want to add there?
I think Alexander did a very good job to explain this. I do have the same view on this, and in general, I think in the future we will see both technologies will have their place in the market. But I do believe that a lot of the high frequency controlling stuff could be done with flow battery as well. If you already have a battery in place, then you do not need lithium for this. So I don't see a lot of hybrid solutions in the very near future for that, because it's just too it's complicated, and yeah, usually the value stacking or use case stacking is not done yet intensively.
Great. I have a question for all of you. Are any of you producing your own electrolyte?
Nope.
No.
We have done our research and we are able to produce it on a small scale, but on a big scale project, we are relying on third-party producers.
Great. All right. This is a European particular question. How do you handle European requirements related to chemical contamination and other safety regulations? Which safety requirements do the VRFB need to fulfill to be installed in Europe?
In our case, for example, here in particular in Spain and in Europe is almost the same. There are the standard regulations for storing acid material or corrosive materials and also toxic, as everybody here maybe knows, that the vanadium electrolyte is corrosive due to the sulfuric acid, but also toxic due to the vanadium salts. So we need to accomplish the regulations of storing corrosive and toxic liquids. So it's not more than that. It's preparing the infrastructure, retaining band, and use the right tanks.
So we have installed our lab in with over 1 MWh in a groundwater protection area. It's some work to do that, but it's a pretty straightforward process. You just need to go through this, and then you get the permission.
Maybe that's anyway a comment to this to the market that actually this kind of technology is pretty much known, because it's all the components and elements are known to the health and safety regulations, to the fire regulations, to the permit regulations. So typically it should be not a big discussions about deploying a VRFB system somewhere, because all the local departments know what it is, because it's clearly clarified. And even if it's toxic or hazardous waste issues, whatever, that has been regulated. And because it's non-flammable, non-explosive, you have no issue with the fire department. So everybody knows pretty easily what we can do. And if there is something like a water protection area, then we also, as a company, we support with studies and we support with information, background information to help the local departments and authorities to provide the permits. So we have deployed multiple times in water protection zones, and we have received the permits for deploying.
Great, thank you all. A question for all of you. How do you collaborate with research groups at universities? Anyone like to take that one on?
In our case, we are collaborating in two ways, mainly with our own funding or particular funding, and also with a public funding with European and national projects. So mainly with private and public funding.
Voith is always open to work with universities or with other research institutes, and of course we give we do have some research institutes that are helping us to doing some analytics and doing some testing, and we're quite happy with that.
Yeah, and on our side, we also have multiple partnership levels, if you will. There are probably 20% of the systems installed have been deployed by universities for testing and for learning the technology. But we also have programs where we actually support research in a way that we actually have some kind of promotions for universities. So actually we spend the money for universities to allow to hire research and scientists so that they can work on this topic specifically. And also we work with some universities where we talk about joint development and or joint commercialization of inventions if they occur. So multiple angles with the universities.
Great. We have some technical questions, but I want to maybe ask one myself first, a less technical question, more about Europe. As you all know, Europe has been very aggressive on combating climate change with the EU Green Deal, calling for net zero by 2050. Tell me how you think those goals will benefit the VRFB market going forward.
Yeah, but I then start. So we see that those targets, and you can see this based on the discussion of the taxonomy, for example, political targets are typically given in line with what the industry can provide and support. I think those targets have been also clearly made to give a challenge to the industry. I think it's up to us. And so if you ask for how it does benefit, it does benefit if we communicate enough. And this webinar is one element of communication to the market that actually we are able to support those climate targets, because in combination with renewables, we can allow for 24/7 green. So if all the EU regulation, the Green Deal approach is to reduce carbon emission, to allow for more renewables, it is all about how you add long duration energy storage to renewables to allow for 24/7 green, either to produce maybe green hydrogen or to allow for a kind of a green 100% green power supply, not only through hydrogen, but not only through power hydro, but also through a combination of other wind and solar plus long duration energy storage. So if we are able to translate those challenges and climate targets into a market communication that with the VRFB technology we are able to support 24/7, then we would benefit. If we just look and listen, then nothing happens and we will not benefit. So I see this webinar as one element to actually turn the business opportunity for us into a benefit.
And Alexander, I'd like to add that we need to be and have a clear communication about the unique circular economy approach that we do have in the VRB with reusing electrolyte, and if we do it do a good requalification, then we have a very low carbon footprint on the battery technology, and this must be advertised in the future to gain the knowledge of the politicians and of the decision makers in the
excellent point.
Europe.
Yeah, if I could add, you're going to see later on in our presentation on sustainability some of those metrics on the carbon footprint of the VRFB and things we're doing as well. So good comment, Thomas. Veselin, anything you'd like to add on that question, or should we move on?
I completely agree with Thomas and Alexander. Nothing to add.
All right, great. Next question. The use of no water consumption has been mentioned today, but what about the risk of water hydrolysis in extreme conditions? Anyone like to take that one on?
Let me start, because there's another question which was mentioned for me for the degradation. So there's some kind of combination. So it's right.
Go ahead. Yeah, thanks.
Yeah. So actually, I use the word degradation, but technically it's wrong. I use it because that's the term everybody uses in the market for battery degradation in lithium. Actually, in flow batteries, there's not that degradation. There is on the hardware maybe wear and tear, but on the electrolyte, there is potential oxidation. And because of oxidation of the electrolyte, which means, water kind of being oxidized, which means oxygen leaving and hydrogen's leaving. So that means there is a little bit less of water in there, and that reduces the ability of the battery to keep capacity and capture capacity. So that is kind of reflected by less capacity in the system. So what the lithium system would be called degradation of non-reversible kind of technical situation. Then in the flow battery, you would have oxidation, which you can make reversible. And the process to make it reversible is that you would rebalance it. So you would add additional water and then you would rebalance it to have the same kind of equal amounts of positive, negative in the tanks. So that is the reason why it becomes reversible. And I'm happy, and I think there are much more persons in this room here to give this more flavor and to give this more technical background. But I think this is the reason why this is a good example why the flow battery, the vanadium redox flow battery, is perfect for reuse and perfect for kind of usability in those areas where, for example, you would have risk of hydrolysis, because then you would actually be able to quickly rebalance this. And we have even developed a system which is an automatic rebalancer. That means there is no need anymore for kind of going up to the side and kind of trying to make the rebalancing locally. So you can do this in the constant operation. So that would be my quick answer. But I would like to ask the others as well to give their comments as well on the benefits of the flow battery system for that oxidation and rebalancing versus the degradation.
Personally, I do see that the degradation is very, very little over the time span, and for some safety topics, you need to have once in a while someone checking the system anyway, and if there's anything wrong, you could do this in your I don't know, bi-year annually maintenance program as well. But from my experience, it's not very frequently necessary, and you need to monitor this, and a good battery management system and energy management system should look on the state of health of the overall battery, and then it's not an issue at all.
From my side, just to add that I agree with Alexander. We cannot talk about degradation as in the lithium batteries or rest of the technologies in the market where we are destroying completely the electrode. Here we can talk about maybe to use the word degradation. We can talk about increasing of the resistance due to some modifications of the materials or electrode, and also some changes in the electrolyte, which are mainly on the oxidation or the hydrogen producing, the hydrogen which is produced during operation. So what we are doing is also limiting the hydrogen, the amount of hydrogen which is produced, and rebalancing the system automatically. By default, we are installing a rebalancing system in all of our batteries. In this way, we are keeping the balance between the two electrolytes, and we are avoiding the small degradation or the resistance increase into the material side.
Great, thank you. I'm going to move on here. We've got just a bit of time left. We have a question from Kurt. Some suppliers of cryogenic and compressed air energy storage systems claim that their spinning machines provide spinning reserve to the grid, that DC-only batteries cannot. Is this a genuine engineering issue, or can electrochemical energy storage devices provide virtual spinning reserve? In short, do grids really need us to build thousands of synchronous flywheels on top of DC batteries or not?
May I take this question? I try to speak a little louder. So in general, this is more a PCS question, and you could, if you have a virtual synchronous machine, it's a control loop for a PCS, and you could do this with any kind of energy storage system as well. It's more a question about the PCS and how to control it and how to have a fast response control loop on that. And if you need to provide energy into this system, then the flow battery is, from my experience, as fast as any other technology as well. I personally have cycled flow batteries in the upper kilohertz range or 2-digit kilohertz range, and it followed perfectly.
Great, thank you. We'll move on to the next question. Go ahead.
Yeah, just want to add here, the spinning reserve, yes, that can be provided technically. I mean, there are possibilities to add a synchronous condenser on a large scale basis as well. That's also possible. So you can make this also kind of independent of the inverter, but in principle, there's enough power equipment available for solving the issue. And in fact, you're correct. It's not the DC battery who does it. It's the power equipment, power electronics who does it.
Great. All right, next question here. Do you think that the increase in power density will play a key role in the decrease of stack dimension and thus levelized cost of storage?
Can you just repeat the question? Sorry.
Yeah. Do you think that the increase in power density will play a key role in the decrease of stack dimension and thus levelized cost of storage?
It's yes and no, depending on how you look at this. Let's start with a no. Depending on the size requirements, of course, and the niche areas you're looking into, density is not that critical. But if you look into overall costs, then density can play a role, because the higher dense the system is, the electrode is, the less material you use for tanks, for other equipment. And of course, that will reduce your costs of the system overall. And then it makes you more future competitive. So in terms of roadmap perspective, density is important. I think because it absorbs a lot of material, and that is also not good for the carbon footprint. It also will kind of have the requirement to increase the transportation cost to ship all these electrolyte. But I think just from a deployment perspective, the size or the density is not that critical. But probably Thomas, who is thinking in gigawatt hours, has another thought as well.
Yeah, I think in general the question is it was the question only related to the stack or on the energy density of the electrolyte as well? Of course, everything that saves material helps, as Alexander mentioned. But in the stack, you always have the trade-off between energy density and efficiency. And so I will follow Alexander's yes and no. So for some applications that are they do not care so much about efficiency, it's higher energy density in the stack with maybe higher losses in the stack would be acceptable. For other applications that are where the efficiency is more important, this maybe is not the best solution. In general, we like to see higher energy density in electrolytes, because then they're consuming less space. We don't need to transport that amount of volume. And of course, as you still have to pump it in the stacks, it would reduce the auxiliary power demand as long as the viscosity is not increasing in the same way like the energy density. So again, a clear yes and no.
Fair enough. Got time for one more question here, and then we'll try to leave the chat and Q&A open for any of our panelists once they're not on the screen here to maybe answer some of these questions. But I think this is a good one. Do you feel the need to investigate the sustainability, the source of the carbon footprint of the vanadium that's being used in the electrolyte that you acquire? Do these issues feature in your decision-making process, or is electrolyte acquisition purely price-driven?
I'm happy to start again. So it's definitely yes. So while we're coming from a price-driven decision, we have, as more we go into a carbon-free approach, as more we go into climate changing approach, our clients are requesting to have a clear understanding of the CO2 footprint of the vanadium, where it's coming from. Like from a sourcing strategy, from a business code of conduct perspective. So that is really a requirement. So we are asking this question, and the more we can choose these areas, then the more we're interested. And I think, I'm not saying yet there is a willingness to pay a premium, but I think whoever is in the market is driven by the metal price index. And therefore, I think the one who can offer this more green and more sustainable and more, I would say, kind of a meeting, for example, business code of conduct requirements, then they will win.
I will totally agree on your statement, Alexander, and I would like to add that what is beginning from this year is totally CO2 free or net zero. And so we take the responsible for our business, and we of course need to provide the answers to our clients. They ask us questions, and we need to know about the CO2 footprint of the electrolyte. And for us, the vanadium flow battery makes, from a CO2 point of view, a lot of sense because of the circular economy, and therefore it's important to know about where the electrolyte comes from.
So I agree with Thomas and Alexander. We're living in a year when the CO2 will get a value, and we can evaluate the cost of how the CO2 footprint will affect of the electrolyte cost. So trying to reduce the CO2 footprint is also some of our main objectives.
Great. Listen, there's still another question in the Q&A and in the chat that maybe the panelists could attempt to answer those here while we continue on. That would be great. I want to thank you all, three of you, for your presentations and your answers to the questions. Thanks to those who participated today for some great questions, some hard questions, but I think some very valid ones. I hope everyone found this panel as informative as I did. I want to thank you all again for joining us today, and hopefully you'll be able to stick around for the remainder of the session.